So I'm going to be talking about some experimental work. So my group at ETH Zurich has been doing some experimental work. So my group at ETH Zurich has been doing lately. So when deciding what to talk about for the conference, I looked at the title and the subject, non-equilibrium quantum matter. I also saw that there was a lot of light-induced superconductivity work. So part of my group does do some experiments where we do drive phonons, but that's typically in model systems at the moment. So it's not so much quantum matter. So I chose instead to focus on some experiments where we actually do look at systems that have some quantum mechanical aspects. But we're doing the driving mechanism in these, since both of the examples that I'm going to end up talking about are metallic systems with spin order. The driving mechanism is going to be a bit more non-specific. So apologies to Andrea, who will be upset that I'm just driving high electronic temperatures for both of these examples. But there are some interesting aspects to that. OK, so both the examples are going to be about basically spin-lattice interactions. And they're going to tend to be things in which we basically are manipulating electrons, which basically drive some kind of spin disorder. And we're looking essentially at the consequences of that for coupling to the lattice. And so sort of to put this into context a little bit, why this is interesting, I mean, one point of interest has to do with these sort of inherently ultrafast magnetic phenomena that have been studied for about 20 years or more even now. So one interesting example of that that's a bit related to the first example that I'm going to give has to do with this ultrafast magnetic domain switching. Basically, these are two relatively recent examples in the last 10 years. So they're still subjects of very active study and still not very well understood. But the basic idea is in both cases, it's not so easy to see that one. But in both cases, what you're doing is you have some kind of material that has a spontaneous magnetic moment. And you are using light to switch between one domain orientation and another of the magnetization. And it's controlled essentially by the helicity of the light under a certain relevant parameter range. Closely related to this, and part of the theory is still sort of not very well understood for those processes, it seems that there is some sort of thermal aspect to the dynamics that are observed, and that has a tight connection to observations of ultrafast demagnetization, which will sort of form the basis for my first example that I'll get into a little bit more later. But that's sort of basically, we think that getting a better understanding of spin-lattice interactions in ultrafast demagnetization has a relationship possibly to understanding those phenomena. Okay. The other idea is basically there are a whole set of materials where interactions between spins, charges, and the lattice are very important. So multifunctional materials like multiferroics. You have, for example, ferroelasticity in principle can coexist with ferromagnetism, and in that case. And you also have a lot of other kinds of materials where spin-lattice interactions actually form the basis of a lot of technologies. So the basic questions there is, can we use manipulation of these materials into non-equilibrium states to sort of either enhance or maybe even suppress these magnetoelastic coupling mechanisms? And what influence do those to non-equilibrium aspects have on the actual dynamics of how fast you can actually use these magnetoelastic things when you're using them, for example, as super fast actuators or something like this. So that's sort of a little bit of context. So I have two examples that I want to talk about in my 30 minutes. The first example is basically an example of the ultrafast Einstein-de Haas effect, and I'll sort of explain what I actually mean by that when I get to that. But that's basically related to spin-lattice transfer of angular momentum during the process of ultrafast demagnetization. And the second example is basically looking at a magnetic shape memory alloy, where basically sort of long-scale deformations of the lattice are very closely tied to the magnetic state of the material, and understanding some of the dynamics of spin-lattice interactions in that case. So first I talk about the first example. So basically this has a fairly long history. So it's sort of this idea of ultrafast demagnetization as a problem for condensed matter physics sort of started about 20 years ago with this paper by Beaurepaire et al. Here. Basically, they were looking at ferromagnetic nickel, and they basically whack it with an intense light pulse, femtosecond light pulse, And what they're using is they're using the magneto-optic Kerr effect, basically magnetization-induced rotation of light, to monitor the magnetization in the sample as a function of time. And so this is actually the sort of trace that they showed in the first paper. It's been done many, many times since on different materials. So it doesn't only happen in nickel, it also happens in iron. Cobalt also shows this, and some more heterogeneous materials also show this effect. Typically, it's related to basically ferromagnets that rely on d electrons, so itinerant ferromagnets it's generally observed on. But basically, you have a suppression or a partial suppression of the magnetization on a time scale of on the order of 100 femtoseconds. And this was a bit surprising at the time because there have been, for example, if you look at a 4F system, for example, and our conventional understanding of the time that it would take for this to happen tends to go into the more picoseconds, nanoseconds regime. So it was initially somewhat surprising that this could happen so fast. So one of the reasons why it's so surprising is that it was very poorly understood exactly how angular momentum could transfer out of the spin system on this very fast time scale. And so on a theoretical level, for example, like things like spin phonon scattering was thought to maybe possibly contribute to that, but not in the magnitude that's actually observed in the actual experiment. So what I'm showing here is sort of the initial sort of experimentalist phenomenological interpretation of this. This was actually what was presented in that original paper. And a lot of, so far the phenomenological aspects of the theory haven't really advanced too far beyond this. It essentially relies on something called a 3-temperature model that basically is breaking up the system into sort of a charge component, a spin component, and a lattice component, and saying that you have temperatures assigned to each one. They basically are, you can sort of split it up into these different components, and then you have some kind of coupling between these different thermal baths. And so the basic data, this is showing like a fit based on that model where you have particular coupling constants. You're saying that the pump laser is sort of very quickly driving a temperature increase in the charge system, and this is coupling both to the lattice and the spin, and also there's a back coupling between the lattice and the spin. And of course, you can essentially fit various things to this model. So the one problem with this model is that, okay, it seems to work to describe the data, but we don't really necessarily know what we actually learn from it because the mechanisms are completely swept under the rug. It's a very phenomenological basis. And even this model has actually, on this phenomenological level, has also been challenged somewhat recently in the last 5-10 years by basically this idea of superdiffusion, which is basically saying that a lot of the component of the demagnetization that's actually seen in the experiment is actually not a local phenomenon, but actually due to differential transport of different spin directions in the system, that the majority carriers have a different transport properties as the minority carriers. And so you get a faster depletion of the majority spin carriers in the system. So just to sort of illustrate that in a little bit more terms, I don't know, the colors don't look so great on this projector, but this is sort of an illustration of what that basically is, sort of the local versus super diffusive transport. Here basically, this is essentially the original model, or actually basically it's a set of ideas that says that basically that in your sample, which is represented by this blue rectangle, you have a certain region of the sample that is pumped by the interaction of this basically very bright infrared laser pulse that's basically delivering energy to carriers somehow. So that's this red region. In the local model, what you're doing is you're modifying the magnetization of just that local area, and you're not really affecting what's going on outside it. Whereas with the superdiffusion kind of model, the idea basically is that you're taking some of the majority carriers and you're pushing them into the unexcited region. And so basically, if you looked at the net magnetization moment of the entire sample, that would be constant. It's just basically sort of a local depletion effect that you have due to the transport properties. So in that case, there's actually a significant difference between the two of them in that case in that, well, in one case, if you looked outside the excited region, you would expect to see changes in the magnetization. Those experiments have been done and suggest that this does play some role in at least certain systems. But the question basically is, can we see evidence of contributions from the local effect? And if we had contributions for the local effect, one key question to answer is, okay, if you're depleting the magnetization in that region, that means over the entire sample you're depleting the total magnetization. Where does the angular momentum go? You know, does it go to the orbitals? Does it go to the lattice? Can we see the time scale and where exactly that's going? And so question is it going to the lattice? Because I'm talking about spin-lattice interactions today. Okay, so the Einstein-de Haas effect, this is basically sort of the basic phenomenon, not thinking so much about time resolution, but you think about like a rod of a ferromagnet, and we're sort of trying to imagine that this rod is basically suspended in air by maybe a wire sitting there that basically allows it to rotate freely if it wants to. Initially, it's going to be at rest, and we're going to say that it's magnetized initially along its axis, so going up. So that's the initial condition. And so we know from basically the Einstein-de Haas effect experiments that if you change the magnetization of the rod, so if you, for example, suppose you came in and you just, with a laser, you just demagnetized the entire thing. So you penetrated over the entire rod equally, and we assume that local demagnetization is a phenomenon, and so we decrease the amount of magnetization. And we assume that the angular momentum has to go somewhere. Eventually, it should go to basically a rotational macroscopic rotation of the entire rod. That's, you know, the conventional Einstein-de Haas effect. What you're doing is you're switching the magnetization to the other direction, and you see the rotation. But the same kind of thing should work if you somehow decrease the magnetization in the spin system completely. That should be made up for by a rotation of the atoms in the lattice on long time scales.
Why no spin precession?
Why no spin precession?
Yes.
Well, the assumption is that we are basically taking the average magnetization moment and decreasing it.
The average,
Right.
longitudinal part,
Yes.
the magnitude can be still the same. It's not the case.
I mean, that could be, but but I mean, if on average. So, I mean, what are you saying? So you're saying that in ultrafast demagnetization, what you're actually inducing is a constant precession?
This is what we are doing in our chemistry, just a precession.
I mean, you can induce precession, but you can actually measure that, whether that's happening. And in the phenomenology that I've gone through, you can't see, I mean, the magnetization moment isn't rotating, it's just decreasing. So you can measure the other components of the magnetization. It's not just spinning around yet. You can do that with other kinds of pumps, but this phenomenon, it's clear that the overall magnitude is decreasing, at least on average. Yeah. Okay, so the angular momentum has to go somewhere. On long time scales, it should go to this macroscopic rotation of the entire thing. What happens on short time scales? Because we're interested in dynamics. So the idea is, suppose that we did this on a 100 femtosecond time scale. All right, so basically, the argument is basically if I'm an atom sitting somewhere, or a small section of this rod sitting somewhere in the middle, it's very unclear to me if everything is local, which way I should be moving, basically, if I wanted to do this macroscopic rotation. Because there's no sort of indication, because in order to know how to move, you need to basically know the boundary conditions of the problem. On a very fast time scale, on a time scale faster than the time that it takes for sound waves to propagate through the system, there's no information basically on an acoustic level for an individual section of the material on how to rotate. And so basically another way to think about it is that the demagnetization process should induce basically a local torque on individual magnetization elements inside the system. And if you look at one particular point in the system, say you look at this particular point in the middle, the torques of the surrounding demagnetized areas, the forces resulting from those torques on a particular element will all cancel to zero, because you have basically equal and opposite forces from the two neighbors. Only on the boundary of the rod will you have an uncompensated force, because on the boundaries you don't have a neighbor that will basically counteract the force from the other side. So basically, these atoms sitting on the edge will see a force that makes it go round, and then that will result essentially in a propagation of a transverse strain wave that on long time scales ends up looking like this. So it's just the same as if you took with your hands the outside of the rod and started to twist it. It's the same kind of force. Basically, you have a force that's applied to the surface that will couple to the interior of the sample. But on fast time scales, this is not such a trivial process because that's mediated essentially by the interatomic forces, basically, that comprise the entire rod. All right, so essentially, the point is that if you do this demagnetization on a time scale that's very fast compared with transverse phonon periods, what that actually looks like is it looks like an in-plane force on all surfaces that have a normal that is not parallel to M. So if you have if your n is your normal and m is your magnetization vector, if you have an n cross m that's not equal to 0, that gives rise to a force, and that force is, of course, going to be transverse to the n because it's cross product. So this leads essentially to a transverse strain wave that will propagate from the surface, and a signature of this will be that the sign of the force, basically whether it's going from the left to the right or right to the left, this vector, will depend on the sign of m, also because of this cross product relation.
So Steve, the rod is entirely illuminated here.
In this thought experiment,
thought
yes,
experiment,
yes.
right? Because otherwise you create a stress and then the stress will.
Exactly. The idea is you somehow uniformly illuminate the whole thing.
So just to make sure
Yeah.
understand, so light does not change angular momentum, right? It just changes condition. That's why you have conservation angular momentum.
Right. Yeah, I mean, there were initially a lot of thoughts that maybe some angular momentum contribution from the light from like re-radiation. So people were looking at radiated components of the electric field because there is some emission. But it turns out that that's very negligible. So that doesn't explain the angular momentum. Yeah, I mean, this is regardless of polarization, this phenomenon. It's independent completely.
Is there supposed to be the inverse effect where you can magnetize what you
There is, yes, you can do that. That experiment was done at about the same time as the original Einstein-de Haas experiment. I think it's called the Barnett effect, if I remember right. Yeah. Yeah, he was American, yeah. All right. Okay. So getting to the time-resolved experiment. So what we're doing is we end up not doing the experiment on a rod that we illuminate because that's a really hard experiment. Instead, what we're doing is we're basically taking a section of the rod, so we're taking a section of the surface, and we're basically that means we're basically looking at a film. And so what we do in the experiment is this is a calculation based on the idea that angular momentum transfer occurs within 100 femtoseconds and is basically following this local phenomenon for basically a layer of iron that's demagnetized with a capping layer that's non-magnetic and a substrate that's non-magnetic. And so,
just from my own understanding, it's not the angular momentum that is being transferred at 150 seconds. So somehow things haven't accelerated yet.
No.
The velocity,
it would have to be, if you can say that, yes, if the magnetization drops in 100 femtoseconds, the angular momentum, there must be a torque on something, right?
Okay, but torque, just one second.
So you can have,
I understand
yeah.
there's a torque, which is a force.
Yes.
But at time 0, the velocity is still 0, and it accelerates.
Okay, it depends on what you mean by time 0.
Let's say
So it accelerates over the duration of the effect.
Right.
So as the magnetization is dropping, then you're applying basically a force on the outer surface of this rod over that time scale. Right, you're giving an angular impulse. But at the end of that, then the angular momentum is there at the end of that process.
Right. Okay,
That's the time scale for the transfer.
From my own education, I really don't understand. I'm not sure very well. What is being, at time 0, what is being conserved? What physical quantity is being conserved? I mean, there's a force.
Angular momentum is being conserved. Yeah.
But the velocity is 0 at time 0. I mean, assume that you quench the magnetism. That you quench the magnetism exactly to 0, and then you have atoms that are not moving with a huge.
No. But if you're assuming that everything happens at time 0, then you have a singularity. So you can't make this argument that the
You can't. Okay,
that the atoms are not moving. Right. I mean, you can, I mean, in principle, you could have an atom that's stationary and then just change its velocity, and then it acquires momentum. And if it's, you know, all the way around the surface, that's an angular momentum because of r cross v.
You change the acceleration, not its velocity. I mean,
Right.
the torque goes from 1 to 2, what's changing is the acceleration working on
I think I need to get on. I may not get to the second part of the talk because of this, but yeah. All right. Okay. We can talk about it in the questions. Okay. So the way we try to look at it in the experiment is we basically want to look at, to see transverse phonons. We can see that with diffraction. It's not an easy thing to do, but it's something that you can do in principle. The basic idea is that you're looking at an in-plane diffraction peak. So you're basically doing diffraction, so you have a surface, and you're basically diffracting from lattice planes that are orthogonal to the surface. So this is called surface diffraction. You're not quite meeting the Bragg condition. You're a little bit off from the Bragg condition. But that's still allowed because if you have a thin film, you still have a little bit of play in the amount of momentum uncertainty that you have. And essentially what you're doing is you're also using the grazing incidence and exit of the X-rays to help enhance sensitivity to this surface effect, because it's actually a very subtle kind of surface effect. So another way to think about that in terms of Ewald spheres and conditions for diffraction, this is just sort of basically if you have the crystal surface like this, basically if you're trying to look at a phonon that has a very small wave vector in this direction, you can make up for that basically by essentially taking a reciprocal lattice vector, adding the phonon, and then you have a momentum transfer to X-rays that you can then see with a detector if you place it up here, and you can see the magnitude of that. So you can essentially look at different Q components of this transverse momentum by basically looking at different points in space of above the diffraction plane. And so this is actually the same technology that people use to do inelastic scattering of various particles. So like with X-rays, it's also kind of what's basically done with neutrons in a sense. But this is, we're basically doing it in the time domain rather than the frequency domain. And so this is the actual sample that we have. We have basically, as I said, an iron film with a non-magnetic substrate and non-magnetic capping layers. This is a plot of the actual signal that we have on our detector, basically showing thickness fringes from the, basically these are interference fringes for the two interfaces here that show basically this, that we have a high quality interface. And so basically what we're doing in the experiment is we take an intensity measure along this what's called a truncation rod, and we look at the intensity of the light as a function of time. And basically the effect of having a transverse or even, any kind of phonon will basically be to modulate the intensity of light, basically of the X-rays that are being scattered up like that. And the period, basically you see in the time domain periodic modulations of the intensity, and that's directly, basically, if you take the Fourier transform of that, that gives you the phonon frequency. So you can actually map out phonon dispersion relations in this way. So this is showing basically some of the data. This is from a simulation, basically showing essentially the magnetic contrast for plus and minus magnetizations and subtracting that. So this is a simulated data, basically showing for different momentum transfer, you have different frequencies showing up because you're probing different parts of reciprocal space. This is essentially the raw data that we actually get from the experiment. We're seeing quite clearly contributions at low Q. There are some weak contributions at higher Q, but they die off quickly. That's mostly due to sort of interface quality effects in the case. So our preliminary analysis, basically based on the magnitude of the modulation that we see here, which has about the right frequency to be a transverse wave, and seems very consistent with that in terms of the magnetization, is that we think that a majority of the angular momentum from a quantitative analysis is going to the lattice in less than 500 femtoseconds. And this 500 femtoseconds is a very generous cap. Actually, Chris Dorrance, my student, will say that it's less than 250 femtoseconds, but I'm more conservative. All right, so basically the main question is basically that we can indeed, for the first time actually, see where the angular momentum goes. So we know that there is a local component to this demagnetization from these experiments because we see the transfers of the lattice. That is not to say that the spin transport mechanism is not important in some situations, but I think it is important to notice that at least in this geometry, that spin diffusion stuff is highly suppressed, basically because of the fact that we have insulators basically surrounding our magnetic material.
I'm sorry, Steve, question.
Yeah.
What you showed here, is that a Bragg peak that's shifting, or is it a structure factor? I didn't quite.
You can't see the Bragg peak because the Bragg peak would appear below the sample horizon. So we're looking at wings to a Bragg peak. So you see basically these. Basically, you know, if you have a normal thin film diffraction, you see essentially a peak, and then you see these bobs. So we're basically looking only at these oscillations up at the top. And so what we're doing is we're basically analyzing intensity changes to these wings, these Laue oscillation wings. And those are sensitive to the phonon.
But is this the periodicity of the window that is changing, or is it the contrast?
The periodicity changes to some extent. What is primarily, though, happening is you see the magnitude changing. But yeah, it's both. It's a bit complicated because you have a longitudinal wave and a transverse wave. And they're both basically, another way to think about it is you have an interface formed by the coherent phonon that's propagating into the depth.
And that's an acoustic phonon that is going.
You have a longitudinal and a transverse acoustic phonon. They travel at different speeds. The longitudinal one is subtracted out in our experiment because we do the subtraction of the two magnetization directions. So you only see the transverse wave. And so that's essentially modifying to some extent where the minima of this thing go.
I got it.
Right?
Yeah, thanks.
Yeah. OK. How much time do I officially have? OK. All right, so I'll breeze through the second example pretty fast, although it's the newer parts and probably the more rough. So this is basically talking about magnetic shape memory alloys. Basically, the phenomenology is that you have a very large magnetic field-controlled structural deformation in these materials. So on the order of 11%. So you can basically have size changes in your lattice on the order of 11% just by applying a few Tesla of magnetic field. You can basically, basically it's sensitive to being in a particular phase of the material typically, and you can, one trick to doing this is you can undo these deformations if you heat it up to this other phase. It basically has various applications currently in terms of like actuator switches. This is actually a video of an actuator, actually the material that I'm going to be talking about, basically showing this is a magnetic pole, this is being switched, this is a thin wire of the material, and this is basically contracting when you switch the magnetization direction. And you can see it's a relatively large effect. So that's just basically 11% contraction that you have from that. That's actually used in certain switch devices. All right, so this material, so this is a nickel, this Heusler alloy, this MnGa material, basically alloy material. The phenomenology is sort of shown here. At high temperatures, you have a fairly high symmetry, what's called an austenite cubic phase. And at very low temperatures, you have this magnetic shape memory phase. So the magnetic shape memory phase is a little bit distorted from the cubic structure. It's tetragonal instead of cubic. But another thing that characterizes it that's actually very important for the magnetic shape memory effect is there's essentially sort of a twinning superlattice formation that pops up. This is one example of it. It depends on exactly what the ratio, what the stoichiometry of the material is. This is the one for what I've drawn here. Basically, you have this thing that basically looks like a periodic superlattice modulation at low temperatures. If you go to in between these two phases, there's an intermediate phase that sort of partakes from both phases. It has the cubic base structure of the high temperature phase, but it already has actually a periodic modulation that's the same, basically very close to the same periodicity that you see in the very low temperature phase. And I should point out that all of these phases are ferromagnetic. All right, so where the paramagnetic phase is much higher temperature than these. All right, so basically this charge density wave structure, this distortion of the lattice is actually thought to be very important for the magnetic shape memory effect in this material. Essentially, it's thought of as basically sort of twin domains that are sort of in a periodic relationship. The current understanding is mostly based on the idea that you have basically twinning that is pinned by a latent charge density wave inside the system. And so what you have is essentially the magnetic shape memory effect comes from the magnetic field induced basically straightening out of these twin domains. And so that basically allows you to have very large changes in the lattice structure just by a relatively small application of magnetic field. So the origin, though, of this modulation and its connection to magnetism are still a bit not super well understood, particularly in what's this intermediate pre-martensitic phase. And so the idea basically in our experiment is it possible to use very fast femtosecond electronic excitation to see basically learn about the coupling of magnetism to the structural distortion, specifically with regard to the pre-martensitic to austentite transition. So this is just some X-ray diffraction data. So as opposed to the experiment that I talked about with the Einstein-de Haas effect, what this is doing is it's basically looking at a point in reciprocal space that corresponds to the superlattice formation by this periodic distortion of the lattice. And so what we're doing is we're basically looking at the intensity of the superlattice reflection as a function of time after electronic heating of the system. So we're pumping with just sort of run-of-the-mill near IR pulses. And what we're doing is we're tracking the structural modulation as a function of time. The reason I'm putting this down is just to show that it's possible for us to drive the phase transition from the pre-martensitic to austentite phase transition. We can suppress the superlattice. The way we see that is we see sort of a character change in the dynamics as we cross a particular threshold boundary. So this is actually a calculation. This is the actual data. You can see basically you have a periodic modulation that has to do with excitation of amplitude modes in the system that drops suddenly and changes periodicity quite radically, which is sort of strongly indicative of a phase transition. That's sort of discussed also in these papers for similar kinds of systems. What we also see with looking at the magneto-optic Kerr effect is we see changes in the magnetization that's sort of similar to what you would see in iron or cobalt or nickel that occur on basically a 100 femtosecond time scale, very fast. So it's another case of ultrafast demagnetization in the material. The magnitude of that drop essentially scales with the fluence. So it's linear in the fluence. So trying to sort of look at these two things together, one interesting thing comes from if instead of looking at the amplitude of the superlattice mode, if we actually instead look at the periodicity of the superlattice, we see some actually quite interesting kind of behavior that I think is relatively new to the world of dynamics in superlattices. So basically we have a regular lattice peak. The superlattice basically forms side peaks that correspond basically to the plus q or minus q in reciprocal space. And what we can do is in the experiment we can look as a function of time at the position of these peaks. So we can see if basically the position of this peak tells us whether the lattice overall is expanding or contracting. The position of these side lobe peaks tells us how the modulation is behaving. Is that expanding or contracting? And what we actually see in this is basically a plot as a function of time of the center of these different peaks. It's actually the data shown there. The solid black lines are showing essentially the lattice peak, which is basically showing very typical behavior for basically thermal expansion. So initially, there's not much going on in the first couple picoseconds. There's a little bit of expansion going on, but it really kicks in at about 10 to 20 picoseconds. If you compare that to the superlattice modulation, you actually see quite different kinds of behavior. So you see that actually changes periodicity on a much faster time scale. And actually, so it basically shifts much more than the lattice in the first 2.5 picoseconds, which indicates that what's actually happening is the modulation wave vector is actually shifting relative to the lattice, and on a very fast time scale. And so this shift is essentially proportional to the incident laser fluence, just like the magnetization drop is, which makes us believe that there might be a connection between the magnetization drop and the shift in Q. And that's supported a little bit by some theory work that was done looking at the magnetic susceptibility as a function of magnetization. So that's what's basically shown here, that shows a magnetization-induced shift in basically the divergent point in the susceptibility that is basically indicating a dependence on the Fermi surface nesting vector on the magnetization direction. So that's what we actually think is happening, that we're basically, by dropping the magnetization on these fast timescales, we're inducing this very small change in Q, which suggests that we are indeed, there is some level of coupling between the magnetization and the charge density modulation, not so much for the amplitude of the modulation, but for the periodicity of the modulation. Okay, so that's where I want to end. So this is just sort of summarizing where we are. So the first experiment, we talked about ultrafast demagnetization, this Einstein-de Haas effect. So I think the further work is, there are a couple different directions that we can go. Of course, we can sort of put more firm bounds on the timescales involved. Another interesting thing would be to maybe look at the inverse effect on a dynamic timescale to sort of exploit this kind of spin lattice coupling in a more soft regime where you're not exciting the electrons to 10,000 Kelvin or so. And the other example was this nickel manganite, which really is sort of one of the first to really suggest that the magnetization and this charge density wave distortion actually may have some kind of connection. And so the question is whether or not, again, some kind of coherent perturbation can further explore that kind of coupling. All right, so I think that's it. Oh,